Okay, so we'll wait a few seconds. So we have finished week 12 of parameterized algorithms, and today we are going to discuss some practice problems from week 12. We are recording this session so that it can be referred to later on, and I will upload this video to YouTube also. So in this session, we will talk about the topic of this week, that is fixed parameter intractability. So here we're going to focus on questions like how it is possible to show or provide evidence that a parameterized problem is not fixed parameter tractable. So in this regard, we will need the notion of reduction. Uh, we have already, I think you have already seen the notion of reduction in the first course on algorithms, which is the standard notion of polynomial time reduction. But here we will need a slightly different notion. And before solving the questions, I will formally write down the notion of parameterized reduction. So parameterized reduction is uh, the notion of parameterized reduction is that it transfers negative evidence for fixed parameter tractability from one problem to the other. Uh, the standard notion of polynomial time reduction used in NP completeness theory is not sufficient for our purposes in parameterized algorithms. So let me first write down the notion of parameterized reduction. So, so parameterized reduction algorithm is an algorithm that takes as input an instance x comma k of a problem A. Let me draw it. So here is a schematic diagram of parameterized reduction. So this is the reduction algorithm. So you feed to the reduction algorithm an input x comma k. So k is a parameter and x as usual is an instance of some problem, let us say problem A. And it outputs a pair x dash comma k dash, where x dash is an instance of another problem, let us say instance of problem B, and k dash is a parameter for problem B. So additionally, some conditions should be satisfied for the reduction to be called parameterized reduction. First is that x comma k is a yes instance of A if and only if x dash comma k dash is a yes instance of B. Okay. So it's an if and only if statement. So if x dash is a yes instance, then x is a yes instance. And if x dash comma k dash is a no instance, then x comma k is also a no instance. So A to B, there is a if and only relationship. This is the first condition. The second condition is that uh, the size, I mean the new parameter size should be bounded by some computable function g of k. So for some computable function g, and the third condition is that this whole process, I mean, this reduction algorithm should not take more than time. So the running time of this reduction algorithm should be some function of k, f of k times polynomial in the input size. So f is a computable function. Okay. So such an algorithm which satisfies all these three conditions is called a parameterized reduction algorithm. Okay. So there is a theorem. The theorem says that if there is a parameterized reduction from some problem A to some problem B, and B is fixed parameter tractable, then A is fixed parameter tractable as well. So let me write it down. If there is a parameterized reduction from problem A to problem B, and B is fixed parameter tractable, then A is fixed parameter tractable as well. Okay. So it is easy to see. So what the parameterized reduction algorithm is doing is it is taking an instance of A and converting it into an instance of B. So now if B is fixed parameter tractable, then given any instance of A, you convert it to an instance of B, and due to the fact that B is fixed parameter tractable and this condition that the running time of this conversion algorithm, this reduction algorithm is also f of k times polynomial in the input size of A, that implies that A itself is fixed parameter tractable. That is the theorem. Now I think we can move to the questions. Yeah. So this is the first question. So let me mark the statements A, B, C, and D. So we are supposed to mark the correct options. Basically, given some statements, we want to decide which of them are true and which of them are false. So let's start with the first statement. So if there is a parameterized reduction from A to B and A is fixed parameter tractable, then the reduced problem B is also fixed parameter tractable. Let's have a look at the theorem in parallel. So this is the theorem we have just seen. So in the theorem it said that if there is a reduction from A to B and B is FPT, that implies A is FPT. But the statement of the question is different. It is saying that if A is FPT, then B is FPT. So the theorem and the statement are not aligned. So maybe we can give it a thought whether the statement is true or false. So let me just redraw this schematic. So this is the reduction algorithm, parameterized reduction algorithm. So here is an instance of A, and it outputs an instance of B, and A is known to be FPT. So you can convert A to B, but whether B becomes FPT or B is FPT, that is not guaranteed, because we only know the running time of the parameterized reduction algorithm, so which allows us to write a theorem like this, but the other direction may not be true. So this is not correct. Let me mark it false. So if there is a next one, if there is a polytime many one reduction from A to B and B is fixed parameter tractable, then A is also fixed parameter tractable. How about this one? So what is the many one reduction from A to B? So the term many one refers to the fact that many instances of problem A might be mapped to the same instance of problem B. Some authors use the term Karp reduction for such a reduction. So the term many one reduction is in the context of the standard notion of polynomial time reduction used in NP hardness proofs. So the statement is, if there is a polynomial time many one reduction from A to B and B is FPT, then is A FPT? That is something we have to decide. So we know for sure that because of this theorem that if there is a parameterized reduction from A to B and B is FPT, then A is FPT. But here they're not talking about parameterized reduction, they're talking about many one reduction, which is nothing but you know the standard reduction used in NP hardness proofs. So but the parameterized reduction is different from the standard reduction because we have these additional conditions that the reduction should uh, respect. For example, the size of the parameter, new parameter k dash, should be bounded by some computable function g of the size of the original parameter. These kind of things may not hold. So although the many one reduction may produce an equivalent instance of B, but such a these additional constraint that the parameter is bounded by a function of k, these things may not be respected. So a standard reduction may not qualify as a parameterized reduction, and therefore we cannot invoke this theorem, and therefore this statement may not be true. Okay, so we'll mark this as false. Let's move to the next one. So if there is a parameterized reduction from A to B such that the unparameterized version of A is NP hard, then B is NP hard. So In the standard notion of reduction, if we have a polynomial time reduction algorithm from a problem A to a problem B, and A is an NP-hard problem, then B turns out to be an NP-hard problem. But in this case, they're saying that, okay, you have a parameterized reduction. So let me write a parameterized reduction as with this symbol, less than equal to sub PR. So if there is a parameterized reduction from A to B, such that the unparameterized version of A is NP-hard. So that is an additional piece of information that not the parameterized version of A, but the unparameterized version of A is NP-hard, then B is NP-hard. So that is uh, not aligned with our concept of how we decide the hardness of one problem using standard reductions. So therefore, because of the additional piece of information, that the unparameterized version of A is NP-hard, this statement turns out to be false. Okay. Now let's move to the next one. If there is a parameterized reduction, that is a typo here. So if there is a parameterized reduction from A to B, and oh, there are two reductions. So this is okay. Maybe we should say if there are. So if there are parameterized reductions from A to B and B to C, then there is a parameterized reduction from A to C. So let us say there are two reduction algorithms. Parameterized reduction algorithm 1 and parameterized reduction algorithm 2. So this takes x comma k, which is an instance of the problem A, and outputs x dash comma k dash, which is an instance of problem B. And this in turn is fed to this parameterized algorithm 2, which produces an instance x double dash k double dash, say, which is an instance of problem C. Then is there a reduction from A to C? That is the question. Is there a parameterized reduction from A to C? So we need, so to decide whether there is a parameterized reduction from A to C, we have to show an algorithm, reduction algorithm, that respects these three conditions. Suppose if we can combine these two algorithms and consider this as one algorithm, then there is an algorithm that takes an instance of problem A and produces an instance of problem C. But additionally, does this algorithm also satisfy these two constraints? That is the question. So it is easy to see that k dash is a function. Sorry, so k dash is bounded by a function of k, and k double dash is bounded by, let us say, let me write it. So k dash is bounded by a function, let us say g1 of k, and k double dash is bounded by a function of k dash, let us say g2. So this is bounded by, so this is equal to, this is a computable function. So this reduction can be thought of as, this two reduction algorithms taken together can be thought of as taking an instance of problem A and producing an instance of problem C, such that the new parameter k level dash is bounded by this computation function g1 g2 of k. So it's a composition of functions. So therefore the second condition of parameterized reduction is satisfied. Similarly, the running time is some, for example, for the, if I write it down, so the running time of the first algorithm, the first reduction algorithm, is bounded above by f of k times mod x to be constant. Now the running time of the second algorithm, let us say first, let us say the first, the function is f1 for the first reductions. Similarly, for the second reduction, let us say the function is f2. So for the second reduction, the input is x dash comma k dash. So therefore, this relationship for the running time will hold. So the overall running time will be this running time plus this running time. And k dash, let's take k double dash only. So k double dash is bounded by this function of k. So the total running time will be bounded by, the sum of the two running times. So we want to show that this is some function of k dash times size of x dash to the some constant. So this part is already fine. So k we can replace by this g1 of k, and x we want to replace by some function of x dash. So what we are going to do is the following. Let us plus replace. So we are going to bound the running time. So this is less than or equal to f1 of k plus mod x to the power, let us say, some constant, let us say this is c1, plus, now k dash we can replace by g1 of k and X dash X dash is the size of the problem instance P. X dash can be replaced by F1 of K times uh, uh, oh right, mod X to the C1, this entire thing to the power at some constant C2. So this turns out to be equal to some function f star of k into size of x to the C1, C2, where f star k is f1k plus f2 of g1k into f1k, isn't it? In fact, it should be less than equal to. Okay. So we have found a bound on the running time, and where we have this function f star of k, and this multiplied by C1, C2 is a constant. So some polynomial in the size of x. So therefore, the third condition of the parameterized reduction algorithm at the running time should have this form is also satisfied. So therefore, this two parameterized reduction algorithms merged together can be thought of as a parameterized reduction algorithm for from problem A to problem C. So therefore, this last statement is correct. So let's move to the next question now. So which of the following are true? Consider G comma K to be an instance of clique with maximum degree of G being D. Then to construct an instance of clique on regular graphs G dash comma K, we create D copies G1 through GD of G, and Vi is the copy of V in Gi. For every V that belongs to the graph, original graph, we create a set V sub V of D minus dVg many vertices and make every vertex in VV adjacent to every other vertex in VV and to every copy Vi of V. So first let us digest what is the statement and what all things we are doing. So what is a clique problem? So when we are saying that we have this instance g comma k of the clique problem, so we are asking that so we are given a graph g and an integer k, and we are asking that does there exist a set of k vertices uh, from this graph g that forms a clique? So it's a yes or no type question. So it's a decision version of the clique problem. So now if additionally we know that the maximum degree of the given graph is d, then we construct an instance of clique on regular graphs g dash comma k. So basically we are creating a graph g dash from g such that g dash is a regular graph. That means for every vertex in g dash, the degree is same. So every vertex in g dash has same degree. So how we are converting g to g dash is the following. So let us say this is some graph g. So we make d copies. So what is d? D is the maximum degree in g. So we make d copies of the graph. So this is the original graph g. So we make d copies of this graph. Okay. So let us say this is g1, this is g2, this is g3, g3. But all these d copies are in fact identical to g. And the ith vertex. So for every vertex v, there is a copy in every uh, copy of the graph. So let us say that these are the copies of a given vertex v in G. So for every vertex that is in the original graph, you create some more vertices. Okay. So for example, if there is a vertex in G, so if degree of v in G, so if degree of v in G is d, that means if v is a vertex with maximum degree, then we don't do anything. Okay, do nothing. But if degree of v is less than d, then you make some new vertices in the graph G dash. How many new vertices? So d minus whatever is the degree of the vertex v in G, that many new vertices you create. New vertices are created in G dash. Okay. So what do we do with these vertices? Make every vertex in VB, so make adjacent to every other vertex in VB and to every copy Vi of V. So you make every vertex in VB adjacent to every other vertex in VB. So if you make 10 new vertices, then you make a 10 clique, and then you also connect each of these 10 new vertices to every copy of the vertex that we have already created. Okay. So this is the one reduction that they have described. So first of all, is G dash a regular graph? So consider a vertex. So now first let us verify if G dash is a regular graph. let's do one thing. So first thing is to verify if G dash is a regular graph. So if consider, okay, so consider a vertex P in the original graph with degree D. So D minus dvg is actually 0. So we don't need to make any new vertices. And you have only created these copies. So for each of the copies of B, the degree remains D only. Okay. So the new degree, basically degree of V in, so degree of Vi in G dash remains to be D. So now consider a vertex V with a degree less than D in the original graph. Less than D. So what happens to the vertices that we introduce? So how many vertices we introduce? We introduced D minus dv of G vertices. So for each of these new vertices, forget each of, so consider each of the copies of V first. So now each of these new vertices is connected to every copy of V, correct? Therefore, the degree of every copy now becomes D minus dvg plus whatever was the degree it had. So let us say the vertex has had degree some D dash, which is strictly less than D. So now the new degree of a copy will become D dash plus D minus D dash. So the degree of a copy in a copy of the graph, and that is in GI, it remains D. I mean becomes D. Now consider, uh, so out of these D minus dvg vertices that we have newly introduced, consider one of these new vertices. So these new vertices are connected among themselves. They form a clique. So that is what the description is. Every may create a set D of D minus dvg many vertices and make every vertex in VV adjacent to every other vertex in VV and to every copy Vi of V. So how many copies are there? There are D copies, right? Every vertex is connected to these D copies. Every vertex is getting at least degree D plus among themselves also they are connected. But how many neighbors they will get? So they will get D minus dvg. So dvg, let us say, is D dash. So let us say D minus D dash minus 1, because it's not connected to itself, it's connected to every other new vertex, plus D. So the total degree now it has is 2D minus D dash minus 1. That is not a regular graph. It does not look like a regular graph. So So now it's probably not a it's definitely not a regular graph. But if G is a regular graph such that the degree of every vertex is T, then this is going to be a regular graph. So now let's look at the statements. The first one, let's mark in ABCD. The first statement says that if in the above reduction from click to click on regular graphs. So actually the reduction is not correct in the sense that the graph G dash is probably, it may not be regular. So in light of that, if it has to be correct, then the graph itself has to be regular. The original graph itself has to be regular, but if the original graph is regular, then the reduced graph will also be regular. And existence of a k-clique in the original graph definitely implies a k-clique in the reduced graph, because in the reduced graph we have copies of the original graph only. And if the original graph, sorry, if in the reduced graph there is a k-clique, that implies a k-clique in the original graph also. But if there is a graph which is not regular but contains a k-clique, then the reduction is not correct. We are not in a position to say anything because the reduction does not look correct to me. So the standard reduction from clique to clique on regular graphs, they do something else. So in the standard reduction, they do the following. So they take t distinct copies, G1 through GD of G, and let Vi be the copy of vertex V in the original graph, in the graph Gi. And for every vertex V, they introduce a set V sub V of T minus TG V vertices and add edges between every vertex of V and every Vi of this thing. So the edges are not added. Let me give it a thought. You introduce D minus DGP vertices and add edges between every vertex of that is going to create a clique and every Vi. So they are just adding edges between every vertex of V sub V and each copy of Vi. So the new vertices among themselves, they don't form a clique. So from one new vertex, there is an edge to a copy of the vertex. So for every copy, there are edges, so D edges. So therefore, the graph remains regular. But in this question, it is a different description. So they're saying that For every vertex v in Vg, create a set V sub v of d minus dvg many vertices and make every vertex in Vv adjacent to every other vertex in Vv, which is problematic. And then also to every copy in Vi. So because of this statement, graph may not remain regular. So G dash may not be regular. So this is incorrect. This is an incorrect reduction, I believe. Anyway, so yeah, we have two more questions for today. Okay, so let's look at the other options before we move on. So in the above reduction from clique to clique on regular graphs, the ES instances of G dash comma K may not map to the ES instance of G comma K. Okay. So assuming that the reduction works. In the above reduction from clique to clique on regular graphs, the ES instance of G comma K may not map to the ES instance of G dash comma K. That is true. This is true. But the problem is the reduction will not be considered correct unless G dash is a regular graph. But if G dash is a regular graph, so I think we may skip this question because I have doubts on G dash being regular in this reduction. Move to the next one. So maybe just we'll take a few minutes break because we're already almost halfway through. We'll just break for a few minutes now. Hello. So let us move to the next question. So this is regarding the partial vertex cover problem. The problem instance is G, K, T, and we are given the graph G. The parameter K is for the vertex cover size, and the parameter T is for the minimum number of edges that are to be covered. The question that we are asking is, if there exists a vertex cover of size K, at most K in G, that covers at least K edges. Okay. So we're not interested in uh, so so it's a generalization of the vertex cover problem. If T is the number of edges in the graph, then we are asking the vertex cover question. So in general, we are asking that whether it is possible to cover T number of edges, at least T number of edges, using K vertices. So let's look at the options. Let's mark the statements as A, B, C, D. The first statement, G, K is a ES instance of vertex cover. So consider the vertex cover question where we are asking whether there exists K vertices that cover all the edges. G, K is a ES instance of vertex cover if and only if G, N minus K is a ES instance of independent set. This has nothing to do with partial vertex cover. So let's say this statement is statement A, and let's say this statement is statement P, that G, K is a ES instance of vertex cover, and this is statement Q, G, N minus K is a ES instance of independent set. So question is, does P implies Y implies Q? So first direction is P implies Q. That means if G, K is a ES instance of a vertex cover of the vertex cover problem, then G, N minus K is a ES instance of the independent set problem. Okay. So if G, K is a vertex is a ES instance, so there is a set of vertices which is the vertex cover. There are K vertices in this vertex cover, and some vertices are outside the vertex cover. So the vertices which are outside of the vertex cover cannot have edges among themselves, because that will contradict the fact that the rest of the vertices is a vertex cover. This we had discussed last class also. That if there is an edge between two vertices which are not in the vertex cover, then the definition of vertex cover itself is violated, because this edge is not covered. So therefore, all the vertices which are not in the vertex cover form an independent set. So these vertices which are outside of the vertex cover forms an independent set. And how many such vertices are there outside of the vertex cover? Vertex cover size is K. So there are n minus K vertices outside of the vertex cover. So this set of vertices acts as a witness to an n minus K sized independent set in this graph. So the existence of a K sized vertex cover in this graph implies the existence of an n minus K sized independent set in this graph. So ES instance of vertex cover implies an instance of independent set with the parameters K and n minus K. So P implies Q is correct. So this is true. So how about Q implies P? So that is If there is a g comma n minus k, yes, sorry, if g comma n minus k is a yes instance of independent set, then is j comma k a yes instance of vertex cover? That is, if there is a set of n minus k vertices having no edges among themselves, which is an independent set. So, do we have a k-sized vertex cover in this graph? So, consider the vertices which are outside of the independent set. So, by definition, sorry, uh, this is not. So, there are no edges among these vertices of the independent set. So, edges are probably among the vertices here. Maybe there are some vertices which could be added to the independent set. But this is definitely vertex cover because all the edges have to be among these vertices which are outside of independent set only. That is what the definition of independent set. Oh, hi.
Hello. So somehow I missed because I was under the impression that it is on 11th and I missed on 11th, so I forgot to. I mean, that it is
Okay,
today.
okay, fine. Yeah. So I had communicated that may not be available today, but then I realized that I will have a good connection today. So the concern was that on Friday I may not have good connection.
Okay. So when did it start? This session?
I started at 6 o'clock as usual.
Okay. Okay. Yeah. All right.
So I'm halfway through.
Okay.
So I can give you some context about what I was discussing. So are you able to see the screen?
Yes.
So we're discussing fixed parameter interactability. So
Mm-hmm.
basically, so our objective is to identify, or rather, given a problem, we want to tell whether this problem is fixed parameter tractable or not. That means given a problem, so for our case, problems are of this form: g comma k, where g is a graph and k is a parameter, and we want to ask whether the problem can be solved in time, you know, some function of k times n to the constant, where n is the input size. Okay, input size in the sense number of vertices or number of edges. So some of the problems we have seen, for example, vertex cover parameterized by the input size, the number of vertices is fixed parameter tractable, but some of the problems are not fixed parameter tractable. And if there is a problem, if somebody gives you a problem and that problem is in fact intractable, fixed parameter intractable, then there is no point spending time uh, to design a fixed parameter tractable algorithm for it. So the first thing we try to see is to decide the hardness of the problem in terms of fixed parameter tractability. And the standard tool to do so is something called reduction algorithms. There are, so in the theory of NP completeness, which I think you are aware of, there are reduction algorithms that help us decide whether a problem is NP complete or not.
Yes.
So here also, given a problem, we'll try to see if we can reduce that problem. So if we'll take an instance of the problem, for an example, let us say A is a problem. We take an instance of the problem and we convert it into an instance of another problem. Okay. So generally, what you've seen, we reduce from known NP complete problems like 3-SAT or independent set. And then if we can reduce a problem which is known to be NP complete in polynomial time to another problem, then that problem is also NP complete, the other problem. So if
Yes.
A is polynomial time reducible to B and A is NP complete, then B also is NP complete.
Right. So here the problem B is at least as hard as the problem A is, because A is getting polynomially reduced into the problem B.
Yes. So if
Right.
somebody can solve B in polynomial time, that would mean that B is also solvable in polynomial time, which is a contradiction.
Yes. Yes. Right.
So, but the idea of parameterized reduction algorithm is slightly more involved. So here there are three conditions that the reduction algorithm has to satisfy. The first condition is as usual that it takes uh, an instance of the problem A and converts it into an instance of the problem B such that an yes instance is converted to an yes instance and a no instance is converted to a no instance.
Yes. And what is K here?
The parameter of the parameterized algorithm, parameterized question. So in parameterized algorithms, we are only asking questions of this form. So given a parameter K, whether a problem is solvable or not. For example, in vertex cover, we ask that whether there is a vertex cover of size K or not.
Okay, so does this mean that before this value of K, the problem is tractable, and beyond this parameter K, the problem all of a sudden the problem becomes computationally difficult to solve?
No, it doesn't mean so.
Okay. Okay, so then this K is something which is given in the question, that does there exist a click of the size more than K, or does there exist a vertex cover of the size less than K, like this?
Yes, yes. So that is a general input. So x comma k is the input, where k is a parameter and x in general is a graph. And we're
Okay.
asking a question. So we're asking a decision version of the question that whether there is a clique as you said, or independent set, or vertex cover of size this much.
Oh, I see. So now, then I became confused with this term fixed parameter tractability. Then, because I was having an impression that its name is fixed parameter interactability, because before this parameter the problem is tractable, and beyond this parameter the problem becomes intractable. Like, say, if we consider the satisfiability problem, then satisfiability problem is solvable for some number of the Boolean literals. But as we grow the number of the Boolean literals in the Boolean expression, then the problem becomes intractable. So, in fact, if it is not the case, then could you please tell the meaning of this fixed parameter tractability in one line?
So what did you say about SAT? Or you said that SAT is tractable for some value. Can you repeat what you said?
Because if we keep the number of the Boolean literals low, then set would be is tractable, because we do have many set solvers available online, and even though those set solvers take the help of the underlying heuristic of the Boolean formula, but uh, still, if we keep the number of the Boolean literals low, then the problem would be solvable.
So when we say solvable, we mean polynomial. What is the running time? So if the running time is polynomial in the input size, then that means it is tractable. So if you have small number of variables, then the running time can still be exponential, but because 2 to the some small number is still small enough, then therefore it's reasonably small amount of time, but that does not mean that it's polynomial time solvable.
Yes, so probably this was not my exact intent to say. Otherwise, what could be the meaning of the term the fixed point tractability? That
Okay. So fixed parameter interactability means there should not be exist. So given the problem, you should not be able to find an algorithm that runs in some function of k into n to the constant. So such a thing is not possible. That is in a crude sense. This is what it means. So the running time, this kind of a running time is ruled out. So not polynomial. So polynomial time is of course not possible. But even if you allow some multiplicative factor f of k, so you allow some more time, which is dependent on the parameter, then also you're not able to answer the question whether it's a yes instance or a no instance.
But then this entire running time is a polynomial, and moreover, this is a linear time, because if f of k, because k is certainly not, k is something which is not dependent on n, I think, or is this dependent on n?
No, no. K is,
So if
yeah, yeah. K is
so if
given.
yeah, please, yeah. So what this k is, can so is this k dependent on n?
The K is given. It need not be dependent on n. It's independent of n.
So then this f of k is a constant kind of the thing, and then I'm multiplying this by n. So then for those problems for which we do have the fixed point intractability, so then if I can bring their running time or in this form, then I mean this will, does this mean that the problem is solvable in the polynomial time?
No, no, no. So K is not a constant. Consider the question. So let us say we are asking the vertex cover question. So we are asking whether there exists a vertex cover of size K. Now we know that this is not possible to answer. So if let us say number of, so G of B is let us say n, the number of vertices in the graph is n. So we know there is no polynomial time algorithm to answer this question. So this is known to be NP complete. So n to the constant time running time is ruled out. Okay. Now if the vertex cover size is n by 10 and I give you, so it need not be a constant or it need not be in it may or may not depend on n, but it is given. So let us say it is given to, it can be given as some constant or some, it can be specified in some way. Some dependence on n can be there. But if I give you some liberty in time, okay, so f of k is not necessarily a polynomial function. So f can be, as we have seen, f can be 2 to the power k or 3 to the power k. So even if I give you that much time, so maybe 3 to the power k times some polynomial in n, so that much time will not be sufficient to answer the question for an intractable fixed parameter intractable problem.
Hmm. So if we bring this, if so somehow probably we could modify the algorithm so that we could bring this parameter out, this 2 raised to the power something. I mean, say if there are exponentially large number of the possibilities, say 3 raised to the power n, then out of those many number of the possibilities, we could bring out a major chunk of the possibilities in the form of say 3 raised to the power k outside the total thing, and then something polynomial remains, say that is fk multiplied by this n thing. So then something polynomial remains. So then I mean, what benefit we derive out of this thing, out of this simplification?
So we are able to say more than saying that the problem is not polynomial time solvable. So when we say that there is a problem which is NP complete, so we mean that a polynomial time algorithm in the input size is not possible. So here we are saying something more. Here we are saying that uh, so given a parameter, so that is the whole point of fixed parameter interactability. So the parameter is given, and we are saying that we won't be able to find the solution within a larger time. So the larger time is of this form. So some function of the parameter times a polynomial. Now this function is not necessarily polynomial. It could be exponential. in the parameter. So therefore, we are able to say that this problem is harder, in some sense, harder than being NP complete. I mean, it takes more time than polynomial, something like that.
Okay, 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 right. Now I understood. Yeah.
So two more things, that the reductions should work such that the new parameter k dash for the second problem should be bounded by some computable by some gk, where g is a computable function. Okay, so the parameter size should not grow too high. So it should not be unbounded. And of course, the running time of the reduction algorithm should be also FPT. So that means some computable function of the parameter times polynomial in the input size. So if these three things are satisfied, then we say that we have a parameterized reduction algorithm.
Yes, I have understood. Yeah, these 3 points, uh, except this thing that so this since we are reducing this x comma k to x prime k dash, so x prime is
Hmm.
at least as hard as the x is. And so, like, say, if we are reducing, say, the vertex cover into the satisfiability problem, then the satisfiability problem is at least as hard as the vertex cover problem is. Or,
Yes.
uh, yeah, so in that way. So, like, so what can we say about this k then? So, does this mean that k dash would be more complicated than k, and even though k dash is the transformed form of k by a computable function, so what can be said about the complexity of k dash then?
Complexity of k dash mean, you mean, so k dash is supposed to be small. So after the reduction, k dash is not supposed to be exponential. It's supposed to be small,
Okay, small or smaller than k or what?
smaller than some computable function of k. So it should not be unbounded.
Okay, okay. Yeah, fine, fine.
And then, as you said, so if you have a reduction from a to b, which is parameterized reduction, and then if p is fixed parameter tractable, then a is also fixed parameter tractable, because using the FPT algorithm for p and this reduction, you can solve a. So you convert an instance of a into an instance of b, and b is known to be FPT, so a is also FPT.
Yes, yes,
So that is the basic context in which we are solving the problems. So
yes.
let's look at the problem that we were solving, the third question we were solving. So I
Okay,
think you
so
already,
yes,
yes,
yes, please.
so you already know, we already discussed the first one yesterday, I mean, in the last session, that, so we said that if you have a graph, so you consider a vertex cover, then the vertices which are not in the vertex cover forms an independent set.
Yes,
Because if there was an edge uh, between two vertices outside of the vertex cover, that edge is not covered, so which contradicts the definition of vertex cover.
yes,
So that was the first question, that if g comma k is a yes instance of vertex cover, that means if there is a k-sized vertex cover in G, then there is a n minus k-sized vertex cover in independent set in G.
uh, yes,
The rest, the vertices which are not in the vertex cover are an independent set.
yes.
Okay.
That's right.
So let us move to the next one. So suppose G is a 5 regular graph. So every vertex has degree 5 and G has an independent set of size 10.
Yes.
So then it contains a partial vertex cover. What is a partial vertex cover? So let me repeat. The partial vertex cover means, okay, so this is the optimization version. So in the decision version, partial vertex cover problem is a three tuple. You are given a graph and a parameter k and a parameter t. And the question is, does there exist a set of k vertices that cover at least t edges?
Okay.
So
Uh,
it is the generalization of the vertex cover problem. So if you set t to be the number of edges, that is the vertex cover problem.
yes. So how will it affect the size of the vertex cover? Because in the vertex cover, we would be finding the minimum number of the edges covering all the vertices of the given graph. Uh,
So if you are just interested in, let us say, some 10% of the edges, then the number of vertices can be expected to be even smaller than, uh, I don't know whether it is quantifiable or not, but we can expect that less number of vertices will suffice.
so
Instead of,
what was the definition of the vertex cover? Was that the minimum number of the edges?
uh,
It
definition of
was,
vertex cover is you want to find a set of vertices that covers all the edges.
yes, the minimum number of the vertices required to cover all the edges of the given graph. Yes.
A vertex cover is just a set of vertices. Now, when you are saying minimum, then you are asking that what is the best we can do.
Yes, right.
So in the partial
So,
vertex cover problem, you are just targeting some portion, let us say t number of edges. So somebody has told you that, okay, I don't want you to solve get cover all the edges. You just give me cover t edges, some 10% of edges, let us say. Then what is the minimum number of vertices that you will need?
yes.
So this problem is a generalization of the vertex cover problem.
Hmm.
So in this case, they're saying that, okay, if we have a graph G, which is a 5 regular graph, so every vertex has degree 5, and there is an independent set of size 10. So let us draw this independent set vertices. So let us say that these 10 vertices are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let us say. And each of them have degree 5. This kind of a thing can happen. So maybe one vertex is neighbor to both 1 and 2. That is possible. This kind of a thing can happen. Now, you are asked the following. Let me finish drawing the 5 neighbors of every vertex in the independent set. So question is, so implication is that if this is the case, then this graph contains a partial vertex cover of size 10 that covers at least 50 edges.
So, yeah, because I'm unable to visualize that, how is that possible that G is a 5 regular graph wherein every vertex is having, say, the degree 5, but we simultaneously we have an independent set of the size of 10. So, because meaning the independent set would be that, I mean, these vertices won't be having any edge among them.
Correct,
So,
correct.
how is that possible that we have the degree of every vertex as 5 and we have 10 vertices, so that none of them is connected to any other vertex. So, uh, because if we are having every vertex as the degree 5, Will this be possible? So we would be having more number of the vertices and not the 10 number of the vertices. There would be many more vertices in this graph.
Yes, that is fine. There could be
Okay.
1 million vertices, but 10 of them are such that there is no edge between any pair of them. So then
Yes.
there could be larger independent set, but there is one independent set of size 10.
Okay. Okay. And now they are saying that if and only if, so suppose G has a 5 diagonal graph, G has an independent set of the size 10. If and only if it contains a vertex, partial vertex cover of the size 10, uh, cover of the size 10 means that they are asking that there would be 10 number of the vertices, which covers at least 50 edges. So yes, so because here every vertex is covering say at least 5 edges. Every vertex is covering 5 edges at least. So therefore, the number of the edges covered is 50 edges have been covered, and the size of the cover is uh, 10.
Yes,
So uh, yeah, so it shows that 10 number of the vertices are covering 50 edges. So
correct.
seems to be okay. Seems to be okay then.
So P implies Q is okay. So let us say this is P. Let us say this statement is P and this statement is Q. So P implies Q is fine.
Mhm.
So now you have to also show that Q implies P. So now assume that there is a vertex cover of size 10 that covers at least 50 edges. Then there must exist an independent set in this graph containing 10 vertices.
Uh, okay. So so if we have say if we have this setup and 10 vertices and then this 50 edges, so can we have an edge in between any two vertices here and which are the part of the independent set we said just now? Because if I consider an edge in between any of the two vertices here, so that will reduce the number of the that will reduce the coverage of the edges.
Correct.
So then we won't be having this thing independent set. Then we won't be having this thing independent set of the size 10. So it shows that the negation of Q implies the negation of P. So but then this would be same as the P implies Q only. Uh,
Let's make an assumption. So let's say Q is correct. So that
yes,
means there is a set of 10 vertices that covers at least 50 edges. Now, you know that it's a 5 regular graph, so no vertex can cover more than 5 edges. So
yes,
essentially, if there are 10 vertices, then 50 edges are, so at most 50 edges can be covered. So because every vertex covers 5 edges, 10 vertices cover 50 edges.
yes,
Now, again, consider that these vertices are numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if there is an edge between any pair of these 10 vertices, then what will happen? One edge will be commonly covered by these two vertices. So that
yes,
means the number of vertices, edges covered by each of them will be at most 4.
yes,
Then the total number of edges covered by this set of 10 vertices will become at most 48.
yes,
So 5 into 8 plus 4 into 2. So
yes,
which is a contradiction. So
yes,
therefore, there cannot exist an edge between any pair of these 10 vertices, which is forming the partial vertex cover. So therefore, this is an independent set of size 10.
yes,
So Q implies P is also true.
yes.
Okay. So you understand what is the two approximation?
Yes. Last time we discussed that. So if we cannot find the exact solution, then we would be getting something which is double of the optimal solution. In case of the minimization problems.
Let's try to do this. I'll push this things down, make some space. So here, when we are saying that there is a two approximation, so then they are considering the optimization version of the problem. So they have t edges to be covered, and they want to find the minimum number of vertices required to cover t edges. And they're saying that if there is a two approximation algorithm for this, so that means if there is an algorithm that uses at most 2 times OPT number of vertices to cover. So let us say let's define OPT. So OPT is, let us say, the minimum number of vertices required to cover T edges in the graph. So there is an algorithm that outputs, let us say, sol is the set of vertices it has output. So number of vertices in sol is at most 2 OPT. Okay.
Yes.
So that is a two approximation algorithm. And so they are saying that a two approximation algorithm is a direct consequence of the fact that at least one of the vertices of any edge must be in the solution. So that is the statement.
So what does it mean that so if we have a partial vertex cover with the two approximation algorithm, this followed by the fact so this thing admits a two approximation algorithm followed by the fact that at least one of the vertices of any edge must be in the solution. So at least one of the vertex of any edge must be the solution. So if we are considering at least one of the vertices of any edge, so then clearly shows that basically we are computing the largest possible vertex cover here. Largest possible because out of the say out of t number of the edges, we have taken at least one vertex out of those t number of the edges. Then we cannot do. I mean, this will definitely find a vertex cover. I mean, all the edges will definitely get covered if we pick at least one vertex from every edge. Then.
Yes, but will it lead to a two approximation? That is the question.
Uh, okay, so will it lead to the two approximation because uh, so yeah so but then this is the largest one. Then two approximation means that we can find something better, and the double of that better is not allowed if we cannot find the exact one. But then this is something we are getting is has to be true. I mean, there is no violation of this. So I think that uh, this is not two approximation, but if I include every so basically the probably the question could be that can I include half of the uh, ages only
No, no,
and
you have to find vertices, not edges.
so can I take the uh, because now I have taken half of the vertices.
No, so consider this graph, which is a star graph.
Mhm.
The minimum vertex cover is which one?
One, but I mean you pick this the central vertex, and this will cover
Yes.
all the edges. So vertex cover is one.
So why do you have to take half the vertices? There could be so many vertices, but maybe the optimal is just one vertex.
But this is according to this question, which says that at least one of the vertices of any edge must be the solution.
Yes, but
So now I have taken t by 2 number of the vertices, and that will definitely constitute a vertex cover. My point is.
okay. So this statement is incorrect, and the reason is the following. So they're saying that because of this simple fact that at least one of the vertices of any edge must be in the solution, the partial vertex cover problem should have a two approximation. The first thing is that we are interested in only covering t number of edges. So at least one of the vertices of any edge must be in the solution is not true. At least one of the edges, sorry, at least one of the vertices of some t edges must be in the solution is correct. So in that
Yeah.
sense,
Yes.
yeah, finding a two approximation like this is not possible. Okay, so so we're not ruling out a two approximation for the partial vertex cover problem, but because of this fact, this is a two approximation is not correct.
Yes.
So this is not true. We'll mark it false. Now this is where I think this statement will make clear your initial doubts on what is a fixed parameter intractability proof. Okay, so an independent set is sorry, independent set is fixed parameter tractable since it is parameterized reducible to vertex cover, which is FPT. So what it is saying that okay, uh, so consider the first statement. First statement says that if you are asked to find an n minus k sized independent set in a graph, you can convert the independent set problem into the vertex cover problem by asking somebody to find you a k sized vertex cover. Because as soon as somebody finds a k sized vertex cover for you, you output the rest of the vertices and declare that you have a n minus k sized independent set. So if somebody finds a vertex cover for you, you can immediately report an independent set, isn't it?
Yes. So probably there is no importance of n minus k here, because just because I mean this is a mechanism that if I can find a vertex cover of the size k, then there would definitely be an independent set of the size n minus k. So where is this parameterized reduction? So where is the reduction of this
Yeah,
parameter?
let's look at it. So what is the reduction algorithm? Somebody gives you an independent set instance. So this is an instance of independent set. So somebody gives you, let's not call it G, let's call it GK only. So a graph and a parameter K. So this is an instance of the independent set problem. Okay, so somebody is asking that can you find me a k-sized independent set in this graph G? So you have a reduction algorithm. You are saying that okay, my algorithm is the following. I let the graph remain as it is. I just change the parameter from q to n minus k, and I declare that this is a vertex cover instance. So if somebody, so you equivalent, so you did not make any changes to the graph. You just change the parameter from k to n minus k. So what is n? The number of vertices. So now you have a vertex covered instance. So the reduction algorithm is nothing, just changes the parameter. Now, if somebody gives you a positive answer, so somebody says that okay, there is actually an n minus k sized vertex cover in this graph. then immediately you say, right, if I will just output the rest of the vertices, that means I will output the k other vertices which are not in the vertex cover, and that is an independent set. That is true. But now you observe the following, that although you can declare that if somebody solves the vertex cover instance for you, you can get the independent set for free, but the parameter n minus k is not bounded by any function of g of k. This is not true. This is not true. Because n could be arbitrarily large. And because n could be arbitrarily large and k could be very small, k could be a constant. Therefore, whatever gk you try to find, n minus k could still be unbounded. And therefore, this reduction, although it is a valid reduction in terms of the standard notion of reductions, that you convert an instance of a problem into another instance of a problem, but this is not a valid parameterized reduction, because the parameter itself, the new parameter itself, is not bounded by any computable function of the old parameter.
Yes, yes, yeah. Now I understood. Yeah. So the meaning of the K prime thing. Yeah.
Yes. So we cannot say that because vertex cover is FPT. So we have seen many algorithms where vertex cover was solved in 3 to the k times n to the constant time. So vertex cover was fixed parameter tractable, but that immediately does not imply that independent set is also fixed parameter tractable. So therefore, this is false.
Yes.
So it is not reducible. It's not parameterized reducible at all. It is reducible, of course. Independent set is reducible to vertex cover, but it is not parameterized reducible to vertex cover because the parameter itself becomes unbounded.
Yes. Yes. This is very good question. Yeah, I understood the crux of this thing, the definition you told in the beginning of the session.
Right, right, right. So we have few minutes. So I'm thinking, what should I do? Let's see how much we can do. So there are a couple of typos in this question. I'll just fix the typos on the go. So in the previous session, we have seen in the context of matroids how we have set systems defined. So we have an universe, set of elements, which is called a universe. Let us say U. And in the universe, we have certain, from the universe, we create a family of sets. So we take some subsets of the universe and say that these are the ranges, and these ranges constitute a family. Okay. So here also consider this set system U comma F. So U is the universe and F is the family of sets from the ground set U, and additionally a parameter K. So the set packing problem UFK is such that we have a family F of subsets of the finite universe U, and the question is to find K pairwise disjoint sets in F. So for example, here this set and this set is pairwise disjoint. So there are no
Yes.
common elements. So therefore, if the value of K is 2, so then it is a yes instance that yes, there is a set of two pairwise disjoint sets in it. So that is the set packing question, that given a universe and a family F of subsets of the universe, you are asking whether there exists a set of K pairwise disjoint sets in, whether there exists K pairwise disjoint sets in the family. How many sets can be packed disjointly? That is the question, set packing.
Yes.
Okay. So now,
Uh,
yes,
no, please continue. Yeah.
so there is so they've defined some instances, and then they're asking that, okay, if we define some instances, whether it's a yes instance of set packing or not. So they've defined 1, 2, 3, and 4 instances. Very simple, but there are some typos. For example, this should be for every vertex. And
So in the first option, we are asking, uh, let's suppose GK is an instance of the independent set. For every edge E in the G, we create a subset consisting of all the vertices that are incident on any one vertex of E. Then G comma K is a yes instance of independent set if and only if uh, this thing is a yes instance of the set packing. So we have been given F as the family of what? F is the collection of all the edges E. And what this E here is, so E is the all the vertices that are incident on any one vertex, all the vertices that are incident on all the edges, something should be else. So this there is another typo, I think, in the option number one, that FE consisting of all the edges that are incident on any one vertex of E.
what is the
What,
typo?
so what this FE here is in the first option, when they write that we create a subset FE consisting of all the,
So if E is for a given edge, let us say this is E. So
yeah,
all the vertices that are incident to either of the endpoints of E. So that is f of E.
okay. So is a yes instance of the set packing. So if we find the independent set of the vertices, so G comma K is an instance of the, so we find the independent set of the size K here. If and only if I can find independent set of K, so all the vertices, and then I consider all the vertices here. And if there are, can I form? So this is a collection of all the vertices, and for every edge of the independent set. If GK is an independent set, so yeah, so so this comprises of then all the vertices. F comprises of all the vertices which are incident on any of the edges.
Okay, so for every edge you have a family. Look at it this way. So in the
Hmm.
graph, you consider an edge. So now there are some vertices which are incident to one endpoint, one of the endpoints of that edge. So that constitutes one family. Now for every edge you have these families. So the claim is if there is a k-sized independent set, then you can find k disjoint such families in the graph.
So since I am having the an independent set of the size k, so there has to be k number of such vertices in which I do not find any edges in between. Uh,
Hmm.
so so therefore
Let's
there has to be the k number of the disjoint sets which are not the part of uh, which do not come together. I think I mean to say.
so let us say this is the graph. So let's take even smaller graph. That is even better. We'll just obtain a counter example. So let's take a small graph. Let us say 1, 2, 3. This is the graph.
Yes.
So an independent set, let's k equal to 2. Okay.
Mhm.
So an independent set IS is 1 comma 3 because 1 and 3 are not connected by an edge.
Mhm.
So there exists an independent set of size 2. But does there exist a set of two families which are disjoint? Now, how many families are there? For every edge, there is a family. Let us say this is edge E1, this is edge E2. So the family corresponding to E1 is all the vertices which are incident to either one or uh, vertex 1 or vertex 2. So 1 is incident to 2, 2 is incident to 1. This is the family corresponding to E1. I should say family corresponding to E1. And there is a family corresponding to E2, which is 2 and 3. Now, there is no other family. This is one family, and this is another family. So in the universe, you have these things. This is one family, this is an. Now, these two families are not disjoint because 2 is common. But whereas the claim is, because there is an independent set of size 2, there should exist two families which are pairwise disjoint. But that is not true, that we can immediately see.
Yes. Yes.
So we will
Yeah.
mark it false. Now let's look at the next one. So I have picked the typos in the next one. So suppose G comma K is an instance. There you go. Is an instance of independent set. For every vertex in the graph, create a family consisting of all the edges that are incident on P. So for every vertex, you consider all the edges that are incident to that vertex. That is one family. So for every vertex, you have one subset. So now the claim is if there is a k-sized independent set in the graph, then there are k disjoint subsets in the family.
And this time, the we are looking for the disjoints of the edges and not of the vertices.
Yes. Now consider
So
that the k vertices of the independent set first. Let us say these are the vertices of the independent set. K. So there is a k-sized independent set. Now you can proceed.
yes, so we do not have edge among these
Yes.
vertices. So since we do not have any edge among these vertices, so then what this FV comprises of? So FV consists of all the edges. So there could be indirect edges, but not the direct edges. So FV consists of all the edges which are incident on these vertices. These many edges are there. So yeah, so now we view it from the set packing viewpoint. So can I find the K mutually disjoint set of the edges? So
Yes.
so the set of the edges here are uh, mutually disjoint are visible.
Yes.
Yeah, so they are
Yes.
mutually disjoint from this
Because
diagram.
if there is so each of the vertices of the independent set, the edges incident to them are disjoint because if there is an edge which is incident to both, let us say 2 and 3, or if there is an edge which is incident to uh, two vertices of the independent set, that contradicts the definition of independent set. So by definition, there cannot exist an edge between two vertices of the independent set. So therefore, all the edges incident to the vertices of the independent set, they are forming essentially disjoint sets. So we can pack k such sets of edges, leading to a k-sized set packing instance. So therefore, this is true.
Yes, yes,
The
yes,
other direction is also similar. It's an if
yes.
and only if statement. So you have to show both the directions.
Ah, yes, yes, yes.
Well, there's some more typos are there. Let's fix them. Uh, it should be edges. Now it's fine.
Yes. So now this is an instance of the vertex cover, and so for the vertex cover, what this FV here comprises of, it is a set of all the edges that are incident on the vertices. So whichever vertices are the for every vertex. Okay, so we get a subset consisting of all the edges that are incident on the vertex V. is an instance of. So are we considering all the vertices in the graph? Then what this FV comprises of all the edges incident on the vertex V. Okay. Then GK is a yes instance of the vertex cover if all the edges, and then this FV, and then the VG and FV is a yes instance of the set packing, because here this FV itself comprises of all the edges.
So f of v is a set of it's a family of the edges. So now for every vertex in the graph, there are some edges which are incident to it. So for every vertex, there is a member in the family. So all the edges incident to them forms a member.
So then all the edges, this EG here would be same as this FV would be same as EG here then, because if we consider all the edges that are incident on all the vertices of the given graph, so then this will include
So
all the edges of the graph.
you are confused because of this union symbol. So F is a set of different sets. Okay, so it should better be written like I think just let me give a thought how it should be written.
So because
It's
otherwise,
comma separate. It's comma separate. So FV for every vertex you have a FV. Now you have the FV1, FV2, FV. How many vertices are there? FVN like that. So this is not a union. So for every vertex you are taking a set. What set? The set of edges incident to that vertex. Now there are n such sets. Now that is the family.
oh, I see. Okay, all right. Yeah, now I understood. Fine. Yeah, so their FV is the set of all the edges. Fine. Incident on the different vertices.
Yes.
Okay. So now this G comma K is a vertex cover of the size K. So there are K number of the vertices covering all the edges. So if we have K number of the vertices, all the edges, covering all the edges, right? So it means that, and if I create the different families, so then since all the edges have been covered by these many vertices, so it won't be possible to find the mutually disjoint uh,
Correct.
sets in F. So this is false.
Right. So for an example, see if you have a vertex cover, uh, so in this case, the vertex cover is one vertex. That's vertex two. So this is a vertex cover. So that covers both the edges. Now, for every vertex, you are taking the edges incident to it. So these two edges are corresponding to this vertex. This edge is corresponding to this vertex. This edge is so in this case, we are able to find because this is disjoint from this. But
So here you could find, so because you only considered what you only considered, say, two edges, but in fact this has to be a family of there has to be three families. One family corresponding to one comprising of the edge E1, another for the vertex 3 having the edge E2, and third one is for the vertex number 2 and having the family as E1 and E2.
yes,
So, so yes, so therefore we do not find any mutually disjoint families here. There would be overlapping. We are not
no,
having, say,
this is one family. U1 is one family. It is one family. Anyway, there is only one family. So every family is independent. So let's take a graph where maybe there is a larger vertex cover. So for example, if I consider another edge E3, So the vertex cover size is now 2. And
Yes.
now what will happen? Let us say, no, so vertex cover size is, so 1 and 2, yes, so
So
1 and 2 is
here
the vertex cover.
1 and 2 is the vertex cover, right? Right. Yeah.
So one family is family corresponding to 1, so that is E1, E3. Another family is family corresponding to 2, that is E1, E2. Another family is family corresponding to 3, that is uh,
E2
E2,
and E3.
E3. So now there is no
No,
disjoint
no, yeah,
families.
no mutually disjoint families of the size 2.
This is a counterexample. Yes. So one in
Yes,
yes instance for the vertex cover leading to a no instance of the set bagging problem.
yes, this is false. So only last one is remaining, even though you are six. I mean, it's six minutes over, but yeah, only last option is remaining. And this GK is a vertex cover, and for every edge E in G, we create a subset consisting of all the vertices. This time it is vertices only, and that are incident on any one vertex of E. That are incident on any one vertex of E, or what? Any one vertex of E. So what this FE here is, this is or ages or what? Or is this correct? Or,
It's a set of vertices
so FE is a
corresponding to
set
the
of,
edge. Yes. So for
okay,
every edge, the vertices which are incident to one of the endpoints. So this is also like the previous one. So in this case, for example, the vertex cover size is 2. It is a 1 and 2. And the family corresponding to the edge E1 will be, in fact, the 3
one
is,
and two, one and two.
so 3 is incident to 2 and 1 is incident to 2, 2 is incident to 1. So all of them. Similarly, the family corresponding to E2 will be 1, 2 as well as 3, all of them. E3 will be 2, 1 and 3, all of them. So we won't be able to find disjoint sets in the family.
Yes, yes,
So this is also false.
yes.
So that is the end of this question. So I think this was the last week of this course, and I don't know if there will be an additional session, but what I have been told initially is that there might be one summarizing session. So if there is any communication from NPTEL, then I think there will be an announcement, then we might meet once again. But officially, this is the end of the course.
Okay, and this is such a fantastic, yeah, problem solving sessions, and this strategy is absolutely right that you used to give a summary in the beginning, and so even if someone has not seen the videos, so that would be really very helpful for him to answer the questions. And so I have a query that do you take more solving sessions of other subjects also in NPTEL?
So right now I'm not taking, but next semester I will take one more. I mean, every semester my plan is to take one problem solving session for one course. So some course related to algorithms.
So like for which subject you would be taking solving session next semester?
So that is not known beforehand to me because the courses that will be offered by NPTEL, that is probably not decided. So that will be communicated to us. Then I will choose one of the courses. That is the plan.
Yeah, so yeah, all your sessions were really too good, and I learned a lot in your
Okay.
sessions.
Yeah,
Thank
yeah.
you so very much. Yeah.
Thank you for joining. You were very consistent, and it was a pleasure to interact with you.
Thank you so much. Good night.
All right. Good
Bye bye.
night.